I'm proud to introduce our University of Maryland colleague who's going to be the seminar speaker, the colloquium speaker today, Dr. Matt Landreman. And so just a bit of a background. Matt got his BA in physics from Swarthmore, and then he went as a Rhodes Scholar to the University of Oxford, where he got his master's degree. Then he came back and got his PhD at MIT. After finishing that, DOE convinced him to stay at MIT as a postdoc for a couple of years. And then in 2013, he came to the University of Maryland as a research associate. And he's marched up the ranks, and he's now a research scientist in ireap. So Matt has become basically a world leader in stellarator physics. And he has, his reputation is such that in 2022, he became the deputy director of a Simon Foundation collaboration on hidden symmetries and fusion energy. He's a fellow of the APS, and he's going to tell us what stellarators are all about today, plasma turbulence and stellarators. And he's also going to convince us that machine learning actually does something for us. I've been a skeptic of that, but he's going to try to convince us today. Anyhow, plasma turbulence and stellarators, physics insights from machine learning.
All right, thanks, Jim. Let's see, is the audio okay? All right, great. Well, thanks to the Colloquium Committee. I really appreciate the invitation to come down here and tell you about some of the work that our group has been doing in ireap here on campus, just a few blocks away. Now, a lot of the work in our group over the last few years has been motivated by this device called a stellarator, which Jim mentioned. And this spinning thing on the screen is one example of it. So essentially, it's a configuration of magnets that uses careful shaping of the magnetic field to confine charged particles and plasma. In the first part of the talk, I'd like to tell you a little bit about what a stellarator is, what some of the applications are, and why they're interesting from a physics point of view, what some of the open physics questions are that we're looking at in our group. And I also wanted to get a little bit more into the details of one particular recent project we did. So thinking about which project would be best to show here. I settled on this recent paper from last year about trying to understand how turbulence in the plasmas that are confined in these magnetic fields, how that turbulence and the magnitude of the turbulence depends on the shaping, depends on the geometry. So the reason for choosing this one is that, like, as I imagine many of you are, we're looking at all these methods and software packages and techniques out there in machine learning, data science, and wondering, okay, is there anything that we can take from those tools to actually do some science and take a step forward and do something that we couldn't do before? So this project was sort of an experiment to see what we could do. And I think we found a use case where using interpretable methods for machine learning, at the end of the day, you get an analytic formula that involves operations on the magnetic field vector, and it's something you can look at and go back and do traditional pen and paper physics analysis with. So it's a method that I think allows some of these new techniques to work in concert with more traditional physics approaches. So even though this paper is one specific set of calculations we did in the context of plasma physics, I'm hoping that you'll be able to leave the seminar with maybe some ideas about how some of these methods could be applied to your own data sets and your own application areas. All right. So let's begin by saying a little bit more about what a stellarator is and the applications. Essentially, a stellarator is a way to confine charged particles in plasma using careful shaping of magnetic fields. You've probably come across situations where charged particles are confined by magnetic fields. There are many situations. One, for instance, is in the dipole fields around planets. There are energetic particles that are confined, like the Van Allen belts around the Earth. Magnetic fields are at least part of what is used to confine particles in a variety of different laboratory traps, like the one shown here. And magnetic fields are also used to confine higher temperature plasmas in the laboratory, both for basic plasma physics studies, for laboratory analogs of space plasmas, and for very high temperature plasmas relevant to fusion energy. So stellarators can be applied to these latter two cases. The basic principle of confining charged particles with a magnetic field is one that students probably encounter the first time they learn about the Lorentz force. If you have a charged particle in a uniform magnetic field, it will move in these helical orbits. So the motion perpendicular to the magnetic field is very strongly constrained. If you have several Tesla magnetic field, then even with very energetic particles at order 10 kilovolts, the radii of these helices can be very small. So you get very good confinement in the perpendicular plane to the magnetic field. But of course, there's no restriction on the motion in the parallel direction, so you have to do something about that. And the first thing you might think of is just have the snake bite its tail so that you don't have any ends to the magnetic field lines. But the problem is that now you no longer have a uniform magnetic field. So it's a little bit stronger on the inside of the bend, and that causes the helical motion to not quite close on itself, and the particles drift across the magnetic field. And so you lose that confinement in the perpendicular direction to the magnetic field. So you have to do something more complicated to try to cure these drifts across the magnetic field. You can never make them entirely go away everywhere, but there's a lot that you can do to make them average to zero. And so the main idea behind stellarator design, where these bizarre twisted shapes come from, is it's an attempt to make these drifts across the magnetic field average to zero over time. A little bit later, we'll get into a bit more detail about some of the principles underlying how you do that shaping. So as you've seen, a stellarator looks sort of like this. On the outside, there's some kind of electromagnets typically that provide the confining magnetic field. The illustration here is a device called W7X. So this is an operating facility at the Max Planck Institute in Germany. And on the inside of the confinement region, the magnetic field lines lie on these nested surfaces. So it's a bit like a hybrid between an onion and a donut. So you have these layers, one inside the other, and the temperature equilibrates very rapidly on any one of the surfaces. So the innermost surface is the hottest, and you get colder as you go towards the edge. So we call these magnetic surfaces. You don't need to have non-planar magnets. So it is possible to design stellarator magnetic fields with simpler magnet shapes. On the right is a device at Columbia University called CNT that uses just planar circular magnets to confine a plasma. And okay, so why not only use that? It looks a lot simpler. There's a trade-off. So the Columbia facility doesn't get as good confinement as the more optimized configuration at the left. Coming back to some of the applications, so one that's noteworthy is fusion energy. So the basic idea here is that in a high temperature plasma, you could use fusion reactions between isotopes of hydrogen, which give off a lot of heat, and you could envision taking a sort of standard power plant layout, like would be used for coal or gas-fired power plants or a fission plant, and swap out the heat source. So if this could be made to work, there's a lot of potential advantages. basically all the upside of fission. So it's a carbon-free approach. It could provide baseload power. You could use very little land and build these facilities close to the users, close to cities, and the fuel is essentially unlimited. But in contrast to fission, you're not using materials like uranium or plutonium, so you don't have the same proliferation concerns, and the stability is more passive, so you don't have to worry about runaway, and the half-lives of all the materials that are involved are orders of magnitude shorter. There's been a lot of activity in this area in the past, especially in the past 5 years. There have been just an explosion of startup companies, some of them raising, many of them raising order $100 million or a few in the billions. And this has brought a lot of resources and people into the field. Let's see, on the right here is a headline from Science last year, which highlighted some of the companies. So as far as I know, there are 8 startup companies right now that are specifically working on stellarators. Of course, there's many more looking at other fusion energy approaches. And last month in Nature's article about technologies to watch in 2026, they highlighted these fusion startups, including stellarators and W7X. So it's a pretty exciting time for the field right now. And again, like the order of magnitude of money coming in right now is in the billions. So there's a lot of new people and new students, and things are getting built. It's pretty exciting. But as I mentioned earlier, that's not the only application. So a nice thing about stellarators as a confinement concept is that you're not relying on electric fields for confinement. So it doesn't matter what the sign of the charge is. And that means you can confine, for instance, electron-positron plasmas. These are interesting for several reasons. So just from a plasma physics point of view, if you have the symmetry between the positive and negative charges, the spectrum of waves is very different than in hydrogen plasma. And it's expected that you may have electron-positron plasmas in astrophysical settings, like around neutron stars, black holes. So it'd be very interesting to confine these in the laboratory. What I'm showing here is a picture from a stellarator that's being built at the Max Planck Institute to confine electron-positron pair plasmas. The CAD drawing is at the left, and on the right is a recent cold test of one of the superconducting magnets. Our group has been a little bit involved in this design, contributing some software and being part of the design reviews. But it's another exciting application of these devices. Let me turn back now to this question of how exactly do you do the shaping to make these drifts of the particles across the magnetic field average to 0? There's a variety of different ways people think about the problem, but I wanted to highlight one that is quite elegant called quasi-symmetry. So to understand this idea, let's go back to the Lagrangian for a test particle in a prescribed magnetic field. So here A is the vector potential, and x dot's the particle velocity. Now, this gyration of the particles around the magnetic field is very fast. So typically, you may not be interested in the details of that helical gyration. So let's average over that. That gives you an object called the guiding center Lagrangian. So just averaging over the ring to get sort of the motion of the center. And now let's take the resulting Lagrangian, which I haven't written, but you can express it in special coordinates. So in these systems where you have these nested surfaces of field lines, it's natural to use coordinates where one of the coordinates labels which surface you're on, so that's R here, and then you have the two angles, the short way and the long way around the torus. And there's a particular prescription for how best to define those angles to give them physical meaning. So if you express this average Lagrangian in these coordinates, there's a remarkable structure to the Lagrangian in that the position, specifically the dependence of the Lagrangian on these two angles on the surface, enters only through the strength of the magnetic field. So like you started with a field where the individual vector components of A, the vector potential, mattered. And we've ended up through these averaging and this particular choice of coordinates in a place where only the magnitude matters. And it's a lot easier to get a symmetry of the magnitude than to get a symmetry of all the vector components. So it was realized back in the 80s that if you had an ignorable coordinate, basically a symmetry in the field strength, that could give you a conserved quantity analogous to canonical angular momentum of this sort of average motion. And of course, when you have an extra conserved quantity, that really severely constrains the dynamics. So you go from having essentially chaotic particle trajectories to having integrable ones, which allow you to really constrain the motion of the particles and keep them close to where they started. This idea has been around for a long time, since the 80s, as I mentioned. I'll mention our colleague Ted Jacobson had a paper last year sort of going through these ideas with a modern perspective. So if you're interested in more details, you may be interested to look there. And it turns out you can actually find magnetic fields and magnets that have this property. This animation that we saw on the first slide is an example. So the gray curves that are twirling around are the electromagnet shapes, and the blue and yellow region in the middle is where you would confine the particles. So you can see that there's not a continuous symmetry to that rotating blue and yellow blob. But if you snip the torus and unwrap it into a square in these special angles, it looks like this figure in the lower left. So you can see that there's a symmetry direction, and that gives you this conserved quantity and hence the confinement. So you can do the sort of simple-minded check to see, did this actually work? You can put a bunch of particles in this magnetic field, trace their trajectories, and see, do they stay inside? And that's what's shown on the right. So the different curves are different magnetic field geometries. You stick a bunch of particles in there and see, do they leave out the edge of the simulation domain? And I don't know, for devices that were designed before about 5 years ago, you tend to get these traces at the top where the majority of particles are confined, but maybe you lose 20 or 30% of them. So it's pretty decent. That may be good enough depending on what you want to do. But nowadays, in the last 5 years or so, there have been a lot of advances in how to numerically design these magnetic fields. So you can get the lost particle fraction down to 0.1% of what you started. Some of these devices are even not on the scale because they just don't lose any particles, so they don't appear at all on a log scale. This particular design here at the left was work with Elizabeth Paul, who was a PhD student here at Maryland a few years ago. And she's continued working on this in this area and is now on the faculty at Columbia. Now, the story is not at all closed. There's a lot of open questions in the field, and I'd like to try to convey, at least on a high level, what some of the questions are that we're thinking about in the group. Generally, the space of possible plasma shapes is very high dimensional, right? Looking at a few of the different possibilities in this mutating blob here. It's a very high dimensional space, and it's something you can't really explore experimentally because, you can't build one set of magnets that's going to realize all these. So there's a lot of opportunity and need for theoretical guidance, for numerical experiments to see what are the possibilities and what are the principles. I've put up here photos of a couple of people in the group, Rory, who's a postdoc, and Byung Chan, who's a PhD student, and they're working in this general area of trying to understand how do you navigate this space, how do you find the most interesting regions of it, and to know if you're in a good part of parameter space, you can you can investigate things like the details of the particle trajectories. So on the right here, there are a couple of examples. The top is basically bad. You can see that you start a particle, on the colored surface, and it has this complicated chaotic motion and sort of drifts away. So it's drifting out. That's not good. Whereas the device at the bottom, it has a fairly complicated particle trajectory. It doesn't have this quasi-symmetry property, but nonetheless, it looks like the motion is sort of quasi-periodic. It doesn't come back exactly to where it started, but it stays more or less on the edge of the green and red colored region. So this might be good enough. And I think there's a lot that could be done to understand some of the principles about the average motion of particles on different time scales, how exactly are they related to the overall shaping of the magnetic field, and then sort of practically, how do you develop algorithms to find these magnetic fields with these good properties. Probably many of you are thinking like, oh my gosh, these magnets look completely insane. How is this even possible? So of course, that motivates another big direction of research, which is, what are the methods that could be used to make the magnet simpler? They do tend to be the cost driver and most expensive component in these experiments and facilities. So we've done a lot of work in this general area of trying to understand, what are the principles for designing magnets, and how can you make them simpler? A couple of the students in our group, John and Sienna, are working in this area. This animation here is a project, one project that Sienna worked on recently, developing fast methods to calculate the electromagnetic forces on the coils, and in a way that you can differentiate through the calculation and do optimization with it. So it's very hard to do this sort of analysis with like a finite element modeling code and do derivative-based optimization. But there's some really beautiful physics actually that you can do just thinking about ways to do fast evaluation of the like self fields and self forces on filamentary curves, dealing with the singular denominator in the Biot-Savart law, and using asymptotic methods to get fast methods to evaluate those integrals so that you can do very efficient derivative-based optimization. And she was able to show that you can modify the shapes of the magnets to reduce the electromagnetic forces, which makes everything easier to build. Then another very important category of questions related to any magnetically confined plasma is turbulence. So magnetically confined plasmas are essentially always turbulent. And part of the reason for that is that often you're in a situation similar to a pot of boiling water on a stove, where there's some kind of gradient. There's a hot side and a cold side, and so you're not in equilibrium, and that can give rise to convective cells that cause mixing and cause flow of heat from the hot part to the cold part. So it's very similar in a confined plasma, except now the innermost layer of the onion is the hot part, and the convective cells mix the inside with the outside. So a number of people in ireap are thinking about questions like this. I put some of their pictures up here. Ian, who's a research scientist, and Nathaniel and Zheng Yang are PhD students. So some of the general questions related to turbulence are just, how do you model it numerically? How can you make those simulations as efficient as possible? And then what are the levers you have over the turbulence to be able to control it? So if you can reduce the turbulence, you may be able to get higher temperatures for the same energy input. So that is that sort of brings us to the second part of the talk about one particular recent project that I'd like to go into a little bit more detail on, which is understanding how the turbulence in these confined plasmas depends on the shape of the plasma and the shaping of the magnetic field. And in this project, we wanted to see what we could do with machine learning methods and see if there are interpretable methods that could give you some insight and actually do some useful science. It's been known for a while that the turbulence in these plasmas does depend on the geometry. It's sort of anecdotally that was known, but there's not been an agreed upon theory for how that dependence, how to understand that dependence. And if you could understand it, I mean, understanding is great for its own sake, but then also you could use it for design optimization, right? You could factor that in addition to concepts like quasi-symmetry to choose even better geometries for the magnets and for the plasma. A lot of work has been done on developing codes to simulate this turbulence. And of course, depending on the physics fidelity you want, it could range anywhere from millions of CPU hours, range up to millions of CPU hours. But in the past few years, thanks to advances in both the hardware and the software, it's been possible to get simulation times down to a nice spot of order 10 minutes, which is a nice sweet spot because even though it's still expensive, it takes a little bit of time to get a result. It's fast enough that you can do it thousands of times. You can run many, many thousands of simulations to start to assemble data sets and look for trends in the data. These simulations are have to be fairly sophisticated because typically the mean free path in these plasmas is quite long compared to their size. So you get significant departures from a Maxwellian distribution function, and that means you really have to simulate them kinetically rather than as a fluid simulation, like you might do for a global climate simulation. So in addition to the spatial dimensions, you also have velocity dimensions. And we'll come in a moment to why you can get away with 5D instead of 6D. You might notice from the figure on the right that so the colors here represent electrostatic potential fluctuations during the turbulence. And you can see that the structure of the fluctuations is very elongated in one dimension. That's the direction of the magnetic field. So again, because you have no confinement essentially along the magnetic field, there's very rapid equilibration of lots of quantities like the potential and the temperature. But in the direction perpendicular to the magnetic field, you still have these very small structures that can be comparable in size to the gyration radius. Okay, let me show a few equations related to how these simulations are done. The starting point is a kinetic equation. So derivative of the distribution function f along the particle trajectories or the characteristic curves would be 0 in the absence of collisions. You may want to include some collisions. And here we have the Lorentz force as the acceleration. Now, again, this gyration is a very fast time scale, and it's much faster than the time scales on which the plasma quantities like the temperature and the potential fluctuate. So it would be really nice to average over that very fast time scale so you don't have to resolve it. And we've already started to do this, talked about this earlier in the talk with this idea of a guiding center that you average over the gyration. This method of averaging the kinetic equation over the gyration is a topic that our colleague Tom worked on. Many people have worked on this as well over the years to derive these averaged guiding center equations that show how the distribution function of guiding centers. So you could think of now, like, instead of having a gas or a plasma of point particles, you have a plasma consisting of charged rings that move around under these complicated dynamics. And we call this the gyrokinetic equation after this averaging. So now instead of having the particle trajectories as the characteristic curves in your kinetic equation, you have characteristic curves which are like how the center of the ring moves with time due to inhomogeneities in the magnetic field and other effects. Now this is a nonlinear problem because the guiding center velocity, it depends on the electric field, it depends on the magnetic field, And then E and B in turn depend on things like the charge density and the current density, which depend on the distribution function. So this term here is nonlinear, and that's why you can have turbulence. So there's a picture here of Bill Dorland, who, as you know, passed away a couple years ago. And he's worked with us. I've worked with Bill since I came here at Maryland. Bill's best known in plasma physics for being the first person to really simulate this nonlinear kinetic equation numerically, so that you could actually see the turbulence with the kinetic effects. And Bill developed a lot of techniques and codes that are still widely used today. So that's a bit of background on how we simulate the turbulence. Now let's turn to, if you're going to do some data science on big collections of this turbulence, you need a data set. So how do you create a data set of these turbulence simulations? Well, first you need a bunch of geometries. So there's various ways that you can come up with lots of magnetic field geometries. A selection are shown here. So you can have a skinny one, a wide one. You can have different discrete rotation symmetries. You can have different pressures in the plasma and so forth. And nowadays, other groups have started to make online data sets with thousands of these configurations. So coming up with those is step one. And now in all these geometries, we're going to run one of these turbulence simulations. When you do a turbulence simulation, you tend to get some nonlinear chaotic wiggle, like the curves shown here. So these are, each different color is a different magnetic field geometry. Time is the horizontal axis, and then the quantity that's being plotted is the heat flux. So you have these convective cells that are carrying heat from the hot side to the cold side, and you just average and look at, so what's the flux of energy from the hot to the cold. Now, for many applications, you really don't care about every chaotic up and down of these curves. You want to know, like, what's the average? What's the sort of average magnitude of the turbulence? So we'll just average these curves after the initial transient. These simulations and the ones that we used in the study were computed using a code called GX, which was actually written by a Maryland undergraduate. Noah here was an honors program student a few years ago and worked with Bill to write this GPU gyrokinetic code, which is now sort of state-of-the-art in the field. And Noah now works at one of these fusion startup companies. But lots of people are using this code that he wrote as an undergraduate here. So as I said, it's order 10 minutes, maybe a little bit less, to compute the average flux of heat in one magnetic field geometry. So for this study, we ran 200,000 of these simulations, which is actually not so crazy these days. The total charge to our supercomputer account at NERSC was 7,000 node hours. So I think Jim isn't too worried about a charge like that compared to typical scientific simulation budgets these days. And I wanted to show this histogram. So this is a slice through the data set, taking a bunch of different magnetic fields where the temperature gradient was specified to be the same in all of them. So if the turbulence is a higher amplitude or a lower amplitude, it's not because we cranked up the stove on our pot of water. The temperature gradient was the same in all cases, but the horizontal coordinate here is like the magnitude of the turbulence, essentially, the heat flux in a physically meaningful units. And you can see some of these geometries had a heat flux of 10 to the 3 in the physically meaningful units, whereas others had a heat flux of 0 because there was no linear instability. Even with this temperature gradient, they were linearly stable, so there was no turbulence. So that's just showing how the geometry has a lot of effect on the turbulence in these plasmas. All right, so now let's start coming to some of the analysis and thinking about how to answer this question about, like, how does the geometry affect the turbulence. Well, you can start by going back to the gyrokinetic equation, the underlying equation of the system here, and looking at where does the geometry appear. It's not just through vector B, because we've done this averaging over the gyration, and so it turns out that there's several different like vector combinations of components of B that end up mattering. So it turns out that there's 7 of them, and for people who do plasma physics, you might expect some of them, like the grad B drift and the curvature drift, are things that enter. And because we saw it in that picture of the turbulence, it has these very elongated structures. So to do a simulation, you only need to go, millimeters in the perpendicular direction, just a small number of these gyration radii in the perpendicular dimensions. So the magnetic field hardly varies in those perpendicular directions, whereas you might need to go very far along the field line in the parallel direction. So for that reason, all the geometric quantities are really one-dimensional. The information that you supply to a simulation, or like to an analytic calculation of linear stability, are these one-dimensional functions along the field line of things like what's the magnitude of the magnetic field along the field line. Okay, so you might be tempted to open up your book on regression and start trying regression methods, because you're trying to predict the heat flux from a bunch of data. That's a regression problem, but you shouldn't do that too quickly. You can't take these geometric inputs and just blindly apply a regression method to them for this problem, because we want our model to have a physical invariance that's there in the underlying physical system. So in this case, that's a translation invariance. And let me explain what this invariance is. So in the gyrokinetic equation, there's no explicit dependence on like where you are on a field line. Things like the magnitude of B matter. But if you take all those geometric quantities and just shift them along a field line and wrap them around periodically, the equation doesn't realize anything has changed. Everything should be translation invariant. And so you'd like your regression to have that physical invariance built in. Here's an example of this invariance. So what I've done here is run 3 different turbulence simulations, taking all the geometry and then just shifting it some more. The quantities at the left are 4 of those 7 geometric input functions as a function of distance along a magnetic field, and you can see that they sort of shift in lockstep. And then when you look at the turbulence, if you look at the signals of the average heat flux as a function of time on the right, it's chaotic, so they're not identical, but in a statistical average, you get the same amount of turbulence. So you want to make sure that your representation of how the turbulence depends on the geometry has that invariance built in. And if you just go to scikit-learn or something and say, do a regression, it's not going to work, because it's not going to have that invariance property. People in computer vision have paid a lot of attention to translation invariance, because their problems often have that property. If you have some kind of algorithm for detecting cats in an image, if you move the cat a few pixels over, it should still detect a cat. So we can take advantage of some of these ideas that have come up in computer vision, and one of the methods that's very popular there is convolutional neural networks. So this is a particular architecture for neural networks that lets you build in translation invariance. We tried that in this problem, and it worked pretty well. So the left illustration here, for anyone who does neural networks might be able to glean something from this. If you don't do neural networks, don't worry about it. Basically, you have these spatial features go through a part of the neural network that builds in the translation invariance. You also have quantities like the temperature gradient, which aren't spatial, or which don't have this dependence on where you are in a field line. And so you combine that information afterwards to predict the heat flux. The figure on the right shows a prediction for the heat flux from this neural network as on the vertical axis, and then the horizontal axis is you just go and do the direct numerical simulation with the turbulence code. And you can see there's pretty good agreement. And this is for a bunch of magnetic field geometries that were not used to train the neural network. So it is possible to find a model that has the physical invariance built in and very accurately predicts what this nonlinear system is doing. So that's interesting. But the classic problem with neural networks is that they're kind of a black box. You don't know what's going on inside to make this prediction. So that brings us to the interpretable part of the analysis. And our goal here is to get expressions like these ones here, where you actually have a formula involving like the magnetic field vector B and different gradients and things that you can discover from the data and find to be very strongly correlated with the thing you care about. So in this case, the heat flux. I want to tell you about a few different methods we used in this project that have this interpretable character, and that they give you these analytic functions at the end. So depending on how the time goes, we'll talk about Spearman correlation, sequential feature selection, and Shapley values. So let's get into that. They all originate with a approach where you predefine a large candidate library of what your possible analytic functions could look like. This is an idea that's part of several different machine learning methods. And in our case, like we know which geometric quantities enter the physical system we're starting with. So we can start with those 7 functions, which I showed you before. And now you can combine them and do a bunch of different operations on them that you might that are physically reasonable and preserve the invariance. So you could take one of these functions, like the field strength along a field line. You could raise it to some power. You could differentiate it. You could apply some nonlinear function to it pointwise. All of those things preserve the translation invariance. And you can form products between these different input features. At the end of the day, you want to predict a single number. So you somehow have to reduce these functions of space down to a single number to predict a single number, the heat flux. And there's a bunch of different ways to do that reduction that preserve the invariance. So if you have a function of one variable and you take its maximum, that's a translation invariant thing. If you take a Fourier transform and take the absolute magnitude of the coefficients, those absolute magnitudes are translation invariant. So there's a bunch of different operations like that where you can build in this invariance. And now you have a combinatorial explosion of different possibilities from all these different ways to modify your original features. So for this project, we had a library with about 1 million of these possible combinations. And now that you have all these potential features that could be correlated with the thing you care about, the heat flux, now you can start to do analysis with these functions. So a very quick and dirty thing you can do is something called Spearman correlation. It differs a bit from standard linear Pearson correlation in that it works for nonlinear relationships too. Because we're not sure one of these features actually is the heat flux. It may be monotonically related through some nonlinear function. And just checking Spearman correlation is a quick way to do that. So if you have this library of 1 million possible things that might predict the heat flux, let's just check. And you can do this in seconds now. And so this list of different geometric objects here is the 5 quantities from the data set that were most highly correlated with the thing we cared about, the heat flux. And you can see that these are variations on a theme. They're not all exact. They don't all have the same power of every quantity, but it's very clear that there's some kind of robust signal there, that these quantities in some combination are going to be very highly correlated with the thing you're regressing on. Let me explain what some of these symbols are. So theta here is a Heaviside function. this B cross kappa dot grad y is a quantity that in study of linear plasma instabilities is known to be correlated with whether you have an instability or not. So we call it bad curvature. The sign here being like a heaviside function of 1 means you tend to have a linear instability. This grad x quantity here. So x is like, previously I called it r. So it's the label on these different magnetic surfaces. And what that means is that if grad x magnitude is very high, then it means your surfaces are getting really close to each other at some point. So that's kind of interesting because remember the temperature is the same on each of these surfaces. They equilibrate in temperature very rapidly. So if grad x is very high, it means there's some point where the local real space temperature gradient is very high. And that physically suggests like, maybe that might cause more virulent instability. So there's some physical plausibility to the results coming out of this analysis here. I'm not too worried about the B. I think that's a Jacobian. But what's really interesting is that there's a physical plausibility here that maybe something about the linear instability is being reflected in these quantities that are picked out. But if you look at linear instability theory for the system, this quantity grad x isn't actually there. It's like the fastest growing linear modes don't depend on grad x. So this is sort of what I was hoping for. It's a place where by analyzing this data set, there's a pattern emerging, which we hadn't expected. But because we have these analytic functions, you can just go check, like sure enough, it's really well correlated with the heat flux. So it poses a precise question for theorists to go off and do their theory on now. Why is grad x so strongly correlated with the turbulence when it's not there in the linear stability theory? So this is sort of what I was hoping for, something where the data science and machine learning are informing a good question to ask analytically. I don't know the answer, but it's a question we can work on now. Let's see, let me tell you about at least one more method for this interpretable machine learning. So previously, I was just correlating one quantity at a time with the heat flux. But now you can build up multi-feature models in the following ways with this idea called sequential feature selection. So first, you have 1 million candidates in your library, and you individually see which one is most correlated with your heat flux. Now, keep fixing that one. Now you try all 999,999 second features, and you can make 2-feature regression models with these great libraries out there with things like things called decision trees to very rapidly try millions and millions of possible regression models and see which 2-feature model fit the data best. Now you've got 2. Now you can add a 3rd feature, and so stepping 1 feature at a time. As you see here, you can get better and better fits to the data, accounting now for combinations of geometric features that weren't in your original library that you predefined, because they may interact in some nonlinear way. Let's see. You can also do this in terms of classification. You could, that's another common paradigm in machine learning. So you can classify, is this magnetic field geometry stable or unstable? And again, you can build up 1 feature at a time, a model to predict, is the system stable or unstable? And the order in which the features get selected in this process now tell you something about their importance. So the first feature to get picked out is probably the most important. The second feature is less important, but also somewhat important. So let's look at which features got picked out. This is the list of the top 5 features that got picked out from this procedure for the regression problem. And I should say in the library of 1 million features, we also added the temperature and density gradients because physically they should affect the turbulence. And sure enough, the temperature gradient got picked out first. That's a nice sanity check. You expect that physically. The second feature to get picked out was the density gradient, which is another feature that you expect from linear stability theory. You know it's going to be important. So it's a nice sanity check of the method that was identified as important. But now we get to the geometric features that start to get picked out from our library. And these are all interacting in some nonlinear way. But it seems like this quantity in red is very strongly correlated with the heat flux. And it looks very similar to the analytic functions that got picked out from the earlier analysis with just correlating one feature at a time. So that's another nice signal of robustness. And it's contributing to this question about, like, why does grad X matter in this correlation when it's not there in the linear stability theory? You can, because this sequential feature selection approach allows multiple features to interact, you don't get just one from your library. You now can look at interactions with additional features in your library. And there's a signal that the second feature is also correlated with the turbulence. It's interesting in that it, for reasons I won't go into, it looks a bit like a quantity that a couple people in these papers here that I reference have suggested might be correlated with the turbulence. In those studies, they didn't really show that conclusively, but they proposed, you might want to pay attention to this aspect of the geometry. And it's interesting that it seems to be there in the data. So this is another way in which, if a theorist proposes something that might be important to look at as a feature, you can look through the data to see if it's actually there. And this is a totally independent way of arriving at that feature. So if the data tells you something and a theorist tells you something, maybe that's a sign that it's important. Let's see, I think I'll skip this one in the interest of time, since we're coming up on the half hour. So that's a specific application area, a specific application in our area of stellarators. But I hope you took away from that project an idea about, given that it's feasible now to have these enormous data sets in whatever your field is, there are these methods that allow you to not only just have a fast interpolation among your data, or fast black box, way to approximate an expensive simulation. There are ways to extract patterns that you can actually understand, and may stimulate interesting questions to go off and investigate further. At this point, I'll start to wrap up and close with some thoughts about open questions and interesting things to look at. We talked at the beginning about what a stellarator is. So it's this configuration of magnets that is interesting both from the point of view of fusion energy and confinement device for basic science. There's a lot of activity right now. There's a lot of interesting open physics questions to look at. And one of them that we talked about in a bit of depth was this question about turbulence in these plasmas. It's really rich nonlinear dynamics sandbox. And the second half of the talk discussed this method where when you have a large data set, it's possible to actually get some insight. You can arrive at these interpretable functions that actually have mathematical symbols we're used to interacting with, which sometimes are surprising and are, I think, a model for how some of these statistical methods and more traditional physics analysis can work in concert with each other. I'll close with a few open questions that we're thinking about related to this work. In this first pass through analyzing the turbulence data, we didn't look specifically at linear stability. So of course, from traditional physics analysis, linear instability is our bread and butter, because it's something where you can really make a lot of progress with pencil and paper. And we are hoping now to go back through the data set and actually compute linear growth rates for instabilities and see how they fit into this picture of interacting features. How predictive is the linear growth rate of the nonlinear state? Things like that. If you control for the linear growth rate, what other geometric factors contribute to the nonlinear state? I think those are interesting physics questions to look at. These interpretable machine learning methods do pretty well, but they don't quite do as well as the neural networks. So there's something about the neural network layers that are extracting features which we didn't think of to put in our library of 1 million candidates. There's a lot of activity right now in machine learning for methods to look inside a neural network and see what it's doing. And we'd like to try some of these methods to see what aspects of the geometry is our neural network picking up on. Because if we can understand that, then we can put it in our candidate library and we can start to do analysis with it. It seems like there's a little bit of extra gain to be had there. And then, as I mentioned, we're starting to get these questions refined and posed by the statistical analysis. Like, why does grad X matter when it doesn't look like it should matter from the point of view of linear instability? So we're hoping to go back to pencil and paper type analysis to better understand these questions that are arising from the interpretable methods. I'll stop there, and I'm looking forward to talking further in the Q&A. Thank you.
So thanks for the great talk. So does anybody have questions? Yeah.
I have a few questions. Miniature question, then a larger question. So first of all, the neural network that was trained, on what order number of parameters did it have?
These are tiny by the scale of what people do these days. I think these were order of 4 layers or something, and a few hundred neurons. So it's not the trillion parameter models that people do these days.
Not aiming for a ChatGPT then.
No.
Okay. Next question. So if I understood correctly, the loop here was to take these geometries, analytically find the B field values within it, and then feed that further along to the models and use that for the turbulence simulation, and then use that for extracting the feature points, correct? Has there been any thought given to taking that a layer above and considering constructing the geometries themselves, perhaps by some characterizing features to make finite subspace, number of lines, radius about those lines, certain symmetries, and then use something like Bayesian optimization to know where in geometry space to look to get the most stable results?
Yeah, along those lines, a natural thing you could do is once you have a fast surrogate for the turbulent simulation, the neural networks are of course differentiable, and so you can do derivative-based optimization on the geometry now to try to minimize the turbulence, and then you don't have to totally trust the surrogate. You can go back at the end and run the high fidelity direct numerical simulation to check, did the turbulence actually go down? There's activity in that right now. Like I think Byung-Chan, one of the students in our group, just got that sort of running. We haven't had time to really exercise it and do the direct numerical simulations to check, but that's certainly an exciting application of this.
So yeah, Ted.
Start out talking about guiding center approximation and quasi-symmetry, and then introduce turbulence.
Yeah.
How robust are the guiding center approximation and the quasi-symmetry to turbulence? Once there's turbulence, does the quasi-symmetry just get destroyed? And even maybe the guiding center approximation go back? Or do they remain pretty good, and so you can kind of superimpose the turbulent effects on top of the guiding center quasi-symmetry analysis? Yeah,
they're kind of independent orthogonal questions. One way to see that is that the particles whose loss you're most concerned with have a lot of energy. They're superthermal particles, and they are less affected by the fluctuating electric fields. Let's see. They zip through these electric fields very fast and have very large guiding centers that average over the fluctuations. So those particles almost don't see the turbulence, and so you need some property like quasi-symmetry to confine those energetic particles. Yeah, and again, like they average over the fluctuating E and B fields. So I think it's not a bad approximation to treat those as sort of independent.
So, but then, it's like you're saying, on the one hand, you control the motion of the highest energy particles with the quasi-symmetry, but then you also want to control effects related to the turbulence.
Yeah.
So what are those effects, like from a practical viewpoint? How does the turbulence do that for having controlled fusion, let's say?
Well, the thing that's bad is that heat leaks out, right? So if you have a certain number of watts of heat, either from external heating, from fusion, whatever, the bigger your heat flux out is, the lower the temperature, right?
What's the actual mechanism of energy transfer out? So if some energy goes to the outside of the confined region, and then is it radiating away, electromagnetic radiation, or particles flying off, or what's happening?
Yeah, so it's a combination of both. So there certainly is radiation, especially at the far edge where things get cool enough that you can start to have atomic physics. But then also there are particles that just run into solid materials if they're really unconfined, or what you'd like to have is a controlled layer where particles diffuse out of the confinement region and then are directed away from the confinement region into a place where you can dump a bunch of gas so that they cool off before hitting any solid materials. So that, yeah, there's a variety of different mechanisms that the energy comes out. And then of course the neutrons are not confined by the magnetic field at all. So they just stream out and would be captured in some volumetric way.
Yeah, so for them it doesn't matter. The turbulence is not counterproductive to capturing the neutron energy.
Right, yeah.
Yes.
So it's interesting that the machine learning could be used to make things interpretable, but I guess maybe I'm wondering about an extension of this. Like one of the things physicists we love is to identify phenomena, right? Like in our last colloquium speaker, I think Brad Marston was mentioning there are analogs of Kelvin waves or something that he's looking for in plasma accelerators. So do you think machine learning can help like find phenomena like certain kinds of waves or instabilities that could be building towards this turbulence, for example, or this is just left to human? Well, firstly, I guess, do you think that our phenomena, I'm not in this field, so is our phenomena kind of like, is that a useful way of thinking about like the behavior of the system? I mean, of course, there's a goal here, but along the way to this goal.
Yeah, okay. This is sort of related to the question about like, can you see what the neural networks are latching onto and paying attention to? Maybe there's some kind of dynamics in the system that we're not aware of, that we weren't clever enough to think of when defining our library of candidates. So we're not looking in detail at the dynamics within any one simulation. We're only trying to predict the average. So I think that, like specifically looking for some kind of wave that we don't know about, you'd have to actually put the whole time dependent, maybe spatially and temporally dependent simulations into a much bigger calculation. But yeah, it's amazing what these methods can identify. So we think we know what the key linear instabilities are, but maybe there's some kind of nonlinear instability we haven't thought of, some nonlinear structure that we should be paying attention to that we haven't thought of. So that's, I think there's potential to find something there, yeah.
Yes.
So you have a finite data set, and you have your million element library. So there's some chance that you correlated with something random, kind of like p-hacking in social science.
Mm-hmm.
So how robust is the correlation? You generate a new data set and you do your thing. How robust is the correlation?
Yeah, so you always you do all your simulations, but then you put 20% of them away and don't use that for the model fitting. And then once you fit the model, you test it on the held out test data, right? So like one example of that was this figure here. So these were simulations that were not used to train the neural network. So in practice they were originally run around the same time rather than wait until after you fit the neural network. But it's tantamount to the same thing.
So just one dumb question. You talked about power generation at the beginning, and of course, the standard joke was that fusion is 25 years away and always will be. There's been a lot of excitement that this is no longer true. Does analysis of this sort lead to plausibly in the reasonable timescale, lead to the development of viable fusion reactors, or is this more a method of understanding turbulence as just a scientific question?
Well, I mean, there are a lot of really tough challenges. That's for sure. And even if we perfectly understood turbulence, I mean, there's a million other things that need to get worked out. So, you do as much as you can. A lot of really bright people are working on all these problems. We just need every shot on goal we can get. So these are fun problems to think about. They're interesting science, and they have these sort of knock-on applications in other areas. Every plasma in the universe is turbulent. So if we understand something motivated by this application, I think we'll still learn something useful that could be applied in other places too.
Okay.
Yeah. You had said you were skeptical of ML methods. Does this talk convince you?
Well,
One thing I liked about this, and a lot of these talks we've seen over the years, you didn't get a sense that there was any analytic result that came out of that statistical analysis people did. So what I liked about what he was doing was he showed these functions, and then he tried to identify what functions were actually the most important. And to me, that gives you physics insight. So I think this is a big step forward from my point of view. Let me ask you one. You showed all this histogram of these heat fluxes, and some of them were zero.
Yeah.
And yet you didn't show the geometry. I didn't see the geometry that actually had zero heat flux. So is there a reason you didn't show it?
I mean, I've got figures we could look at later. But if you take like the outliers, what simulations in the data set had the highest heat flux and the lowest heat flux, and you look at them, certain properties jump out. So this grad X is one example. Like if you look at the cases where the heat flux was 1,000, they have these enormous spikes in grad X. And if you look at the geometries where the heat flux was 0 because they were linearly stable, grad X is really small. So some of these things you can start to see just using this neural network by looking at some of the outliers. But also once you know what to look for, you can see the patterns that way too.
Okay, so I think why don't we call it quits here, and let's thank our speaker for a very nice talk.